And one of the questions that probably should come up to you as a student is, why is pi a constant? Why is the circumference divided by the diameter of a circle a constant for all circles? It doesn't seem that that should be true, but that's what this whole investigation of pi is all about. So this little presentation is going to be tacked on to the end of a very short presentation that I've already made with me at the light board giving you the idea of, hey, pi is defined as circumference by diameter. So let's take a look at this idea. And let's start with a triangle, but not any triangle, a regular triangle, meaning that all three of the sides must be of the same length and all of the vertex angles must be equal. And if it's a regular geometric shape, it has what's known as a center. If you were to take each of the angles and bisect them, they will intersect at a single point. And that's the center of this triangle at C. From point C, I have measured to some aspect of this triangle. C to D is the distance from the center to one of the sides, the shortest distance to a side. And then the distance C to A is the measurement of the distance from the center to a vertex. So for this particular triangle that we see we have a perimeter of 24.11 centimeters. The distance A to B is 8.04 centimeters. A to B, I'm sorry, so that's the side of this triangle. From the center to the vertex is 4.46 centimeters. From the distance from C to D is 2.32 centimeters. And so what I've done is I've taken the perimeter, which obviously we can calculate, and I'm saying that one of these two measurements, either C to D or C to A, must be viewed as a radius. And so I'm going to double it and divide the perimeter by that, and I get two numbers here. So let's notice that when I do that, I get these two numbers, and now I'm going to play with this triangle just a bit, and notice as I drag this triangle around, giving it different lengths, this idea of perimeter divided by twice one of these measurements, these two numbers are staying absolutely the same. Doesn't matter. So what we're claiming then is that for this figure, there are two numbers that will be a constant from the center of this figure, depending upon how you measure quote unquote radius. And you either get a value of 2.60 or you get a value of 5.2, depending upon which way we measure. Shortest distance into the perimeter or longest distance into the perimeter. All right, so let's hide the triangle, and now let's look at a square, and let's do the same thing with a square. It is a regular figure. I'm going to measure the distance from the center to a side and the center up to a corner. And we see we have these two measurements down here. And if I start adjusting how big this square is, all of these measurements change, but these ratios remain constant. And so we notice very quickly that just like for the triangle, these two numbers are constant for all squares. And the Greeks would have known this. They would have figured this piece of the puzzle out. And so we know for a three-sided figure, the ratio is a constant. For a four-sided figure, the ratio is a constant. But let's go back and look at something. 5.2, 2.6. We're down to 4.0, and we're up from 2.6 to 2.83. Let's go to a pentagon now. And for a pentagon, which is a five-sided figure, I still have this idea of center to side, center to vertex. I get these two ratios. And no matter how big or small my regular pentagon is, the ratios are not changing. But now I've moved under 4. I'm at 3.63, and I'm up from 2.83 to 2.94 with a 5-sided figure. So I'm noticing that these two ratios seem to be getting closer together. Let's move to a hexagon now. And my hexagon gives me the same property that these ratios are fixed, but I'm now at 3.0 and 3.46. So those ratios are starting to get closer together, and part of the reason is the distance from the center to a side and the distance from the center to a vertex, those two measurements are becoming closer to each other, and the perimeter is the same. So as a hexagon goes away, let's look at a decagon, a 10-sided figure, and I can change the size of it, but notice these ratios. And once I get to 10 sides, notice I'm at 3.25 and 3.09. So we now know that as this measurement here, S to T and S to Q become closer, S to T and S to Q, as they begin to get closer, these ratios will get closer. And we can go to a 16 gon, and notice now at 16, we're really starting to come in on, okay, we're getting an object that begins to look very circular, and we're seeing these two ratios are in fact constant and close to each other. And you will notice that pi for a circle does lie between these. And if you go to a 32-sided figure, and let me adjust this, a 32-sided figure, if you take a look at that, if you back away from the screen just a little bit, you're going to notice that looks an awful lot like a circle. And notice what your two ratios are. 3.1, almost 4, 3.15. So you are really starting to narrow down on what is the value of pi for a circle as your object gets very close to being circular. This is why Archimedes would then take off, and, or at least my belief is, this would be evidence as to why Archimedes would ask the question, these two measurements must be the same for a circle because there's no corners. So there must be a single number that we would find, and the question is, what will this number be? And because I really do think that Archimedes was looking at the circle as the limit of a polygon of n sides as n gets large without bound. He didn't have that language, but I do believe Archimedes understood that concept. So this is kind of a primer on why is it that pi is a constant and why in the heck Archimedes would have been doing what he was doing to begin with. Well, he was kind of led to it. He knew it had to work out. He just didn't know what the number would be. I hope this helps.